Hi, so now I'm going to talk about Carter's coefficient. This is a term that's used quite often in machine analysis. It's a term that is approximate, but it can be useful. So the idea is that if you think about the field crossing the air gap, it's not going to be a nice uniform air gap, right? You're going to have slots, stator slots, and you could have rotor slots too. So then the path that the field travels through the air gap is not going to be uniform. So one way that was thought of to accommodate the fact that the air gap field flowing through is non-uniform is to modify the air gap length to account for this non-uniform path. So that's what the idea of the Carter coefficient is. So I'm going to go over it in a couple of pages because I think it's useful to have an appreciation of what this means. So Carter coefficient. So the idea is modify air gap length to account for slotting. Okay. So the peak so the MMF from a winding is given by MMF is equal to the summation of the harmonics times the this factor here that includes distribution and pitch factor and so on. So that's the spatial term, and then we have the current term. So if we had a uniform air gap between the stator and rotor, gee, nice smooth air gap. Then we could say that this MMF, I could call it FA is equal to flux flowing across the gap times the total reluctance. We'll talk about this. We'll talk about this more in another lecture and how to model machines using this. So this flux over the reluctance could be thought of as being composed of an MMF term, 2 times the MMF associated with the air gap, because there's the field has to go back across the air gap, so it's times 2, plus the MMF drop in the stator core, plus the MMF drop in the rotor core. So that's essentially all you have. So this is due to the air gap. This is MMF due to stator core, and this is MMF due to rotor core. Okay. So I'm going to call this equation 1, and this is equation 2. So, but now in reality, the air gap is not nice and perfectly uniform like that. There's going to be some slotting. So in reality, there is slotting. So if we consider the case when there is slotting on the stator only. So let's just consider the slotting effect due to the stator. So we have something like this on the stator, and then this is the rotor surface. So this length here is the slot pitch. This would be the length of where the winding goes, B0, and this is the tooth pitch here. So if we think about how the field would flow, the field will come down like this nicely, but there's going to be some field leakage across from the edges, like so, and then on the other side also. So now let's assume that the field only comes out the sides when it's halfway down. Sorry, not halfway, but when this distance here is equal to B0 over 2, so half of the width. So we're assuming no flux flows if it's above that point, which seems relatively reasonable. And so this here is the air gap G. Okay, so then we have a radius from here. There's a radius associated with this, so we could assume that this comes down in a nice circle. So, and then from here it's flowing straight down. So rather than it curving, we're going to make the assumption that there are two parts to the field when we come across here. It's going to flow down here like that, but then it's going to curve in an arc, circular arc, across this bit, okay? And the same from over here. So this is an approximation, and I'll talk about that more at the end, but we'll take that to be the case for now. Okay? So now So the field is going to go flowing down from this slot down, or it's going to curve around and then come down. So these two flows of the field are in parallel. So then it turns out that then this can be best modeled using permeance, because permeance is 1 over reluctance. So like in electric circuits, if you have things in parallel, it's easy to look at them as being 1 over. So 1 over reluctance is the permeance. So we can then add the terms. So this here is an approximate path. Okay, so that the total reluctance or permeance is going to be P1 plus 2 times P2. P1 is the flow down the middle, and 2 times P2 is the flows on the edges. Right, so we're using permeance because just like in electric circuits, you can find the total by taking the inverse of the parallel terms and adding them, right? So now if you recall, the reluctance, so recall that the reluctance is equal to the air gap divided by mu naught times the area. So in this case, the area here is going to be gamma minus beta naught. So mu naught gamma minus beta naught times L, like that. L is the depth into the page or the board. So that's going into the board. So because the area is the cross-sectional area times the depth. That's what the flux is flowing through. So this is reluctance length over mu naught times area. So then the permeance is 1 over the reluctance. So we have mu naught gamma minus beta naught B naught L divided by G, like that. Okay, and I'll call that equation 5, and this is equation 4. Okay, so now P2. So the permeance on one tooth side. So we have P2 is equal to, let's think about this in terms of a small length. So we have the permeance is the length and the area relationship. So reluctance is length over mu naught area. Permeance is mu naught area over length. So then the length part in the permeance is going to be the gap plus 2 pi r divided by 4, because it's a quarter of a circle around this length. Okay, and then we have to integrate that across this width. It's going to be a varying radius. The radius here r, that radius is varying. So we're going to have to use an integral. So that the permeance of particular r can be written out. So we have that on the bottom we have the length, so it's gap plus pi r divided by 2, right? Because it's quarter circle length. Quarter circle length. Okay, this is equation 6. And now the numerator is the area. So that's the length into the page times the radial distance. So it's going to be mu naught L dr. Okay, so then that's equation 6. So then we can evaluate. So P2 is and I'm gonna let me just do one more step. I'm going to just rearrange this. It's going to do mu naught L2 divided by pi out here, and so then that gives dr divided by 2g divided by pi plus r, like that, because now it's a simpler form. Okay, so then I'll integrate this. So we have P2 is equal to 2 mu naught L divided by pi. Then we integrate from 0 to b naught over 2. Why b naught over 2? Because that's half of this distance, which is the limit of the radius. So we have 1 divided by 2g pi plus r dr. And I'll call that equation 7. Now this can be made into a constant, and then we can evaluate the integral. And when we do that, evaluate it from 0 to b naught over 2, we get out P2 is equal to 2 mu naught L divided by pi log 1 plus b naught pi divided by 4g, like that. Call that equation 8. So that then now gives us the permeance for the second term. So then the total effective permeance is, so we have 8 and 5 into 3, and so then we get P is equal to P1 plus 2 P2, which is equal to mu naught L gamma minus B naught divided by G plus 4 over pi times log 1 plus B naught pi divided by 4g, like that, and I'll call that equation 9. Okay, so that's the total permeance. So now let's assume now that we could replace this with a uniform air gap like this, but we'll call it effective air gap. So the air gap here is going to be different value. what should that value be? Let me write something down. So now, suppose actual slotted surface can be replaced with an unslotted surface with a modified equivalent air gap G sub E. The question is, what value would GE be? So if we think about it, we would have, in this case here, we have an ideal permeance and we have the slotted permeance. So the ideal permeance, what's the ideal permeance going to be? 1 over the reluctance, right? The ideal permeance will be mu naught gamma LE over GE. So that has to equal the slotted permeance, which is mu naught L, what is just L, sorry. The L is the depth into the page. Mu naught L gamma minus B naught divided by G plus 4 over pi log 1 plus pi over 4 B naught G, like that. I'll call that equation 10. So solving for G sub E gives, okay, so the mu naught L's can cancel, and so we get GE is equal to gamma divided by gamma minus beta naught divided by G plus 4 over pi log 1 plus pi over 4 B naught over G, like that. That's equation 11. Or we could write GE is equal to K sub C G, where Kc is called the Socata coefficient. We could, so that, what is the Socata coefficient? So if we substitute 11 into the Kc term, so Kc divided by Ge over G, I'll call that 13. So if we substitute 11 into 13, then we get Kc is equal to gamma divided by alpha minus beta naught plus 4g pi log 1 plus pi over 4 b naught g, like that. Now this is one form of the Carter coefficient. There's a lot of different people have derived different Carter coefficients for different geometries. This one is like this. There are Carter coefficients for geometries that are more complicated looking, like that, for example, where you have two bits coming out. But the same idea exists, that you're changing the effective air gap in your magnetic circuit model. And I'll give an example of a magnetic circuit model for a rotary machine where we use this kind of coefficient. So now this derivation assumed that the field curved nicely around, but that in a circle, semicircle, but that's not really very realistic. It's the flow of the field and the air gap is a lot more complicated. But so Carter actually derived using conformal mapping, a more precise form. I'll write that out here for your reference. So the above derivation assumes flux is evenly distributed along the sides of the tooth to a depth b naught over 2. In reality, the flux is non-uniform. The highest flux is near the surface of the tooth. Using conformal mapping, Carter derived the exact correction as, and wait for it, Kc equal to gamma divided by gamma minus 2 b naught pi, and then that's multiplied by tan inverse b naught divided by 2g minus g over b naught log 1 plus b naught divided by 2g squared like that. for large B naught over G, remember B naught is the slot opening width, then the result reduces to the previous equation. For large B naught over G, we obtain previous equation. And so for that field finite element analysis problem you had to solve for, you also looked at the slotting. Basically, that was what you did. So now, if there is slot openings, if there's slot openings on both the stator and the rotor, then there would be two Socata factors. So let me just write that, and then we'll stop. If there are slot openings on both sides of the air gap, then the Socata coefficient for doubly slotted or salient a machine is Kc would be equal to Ks sub Sc times Kc, where this first term would be the stator, would be due to the stator slots, and then the second term will be due to the rotor slots. And just also note that the Socata coefficient doesn't account for saturation, so you're always going to get a better model from the finite element analysis, but this gives you this can give you quite a good approximate value. Note the Socata factor always approximate, since neglects saturation. Okay? So